Good morning, welcome to Physics World. So far you have learned about what is motion and types of motion and the different physical quantities involved in that motion. And then if you want to move a body, how do you move? You go to a body and you couldn't say that okay, body just start moving. Repeat. If you want to move your body, you can't say that body he can move. Then what you have to do? Take an example. You are in the football ground and you want to move the football. What you do? You kick the ball. That means you have applied a force on the ball to make the body to move. So this example tells you that any body wants to move, you have to apply the force on it. So today our topic is to know about force and the laws behind that. So I am starting the next chapter, chapter 3, laws of motion. Long ago, there were 3 scientists arguing that what is motion and how a motion is described. So in that row, the first scientist was Aristotle. Aristotle is very old and famous scientist, mathematician, philosopher. He, teaching the classes to his people, one of his students asked that how a body is moving, why this body is rest. Then Aristotle told that don't think about the bodies which are at rest. There is no meaning for that. And any body is moving, say a stone is rolling on the ground, it is only because the nature of the stone, it is rolling on the ground, nothing else. And this nature was provided by God. So God created the rules. Because of the rules, some bodies are moving, some bodies are at rest. That was Aristotle's answer. This is very philosophical answer, not scientific one. And later we had another scientist, and he was Galileo. Galileo also researched so much about motion, and he described that every body wants to be in rest or wants to be in uniform motion, and is only because of a property called inertia. So inertia is the word given by Galileo only, but that answer also not completely satisfied to the people. Later we got another scientist who was very famous in his time, and today also we say that he is the one of the legend in scientific history, and he is none other than Isaac Newton. He was a great mathematician and physicist. He was the first scientist who introduced force. He told that each and every body is in motion or it is at rest because of force. If you apply the force on the body, if the body is at rest, it comes into motion. If the body is in motion, it comes to rest. So force is the ultimate factor there which will change the motion of the body. So from that point onwards, from that day onwards, from that moment onwards, we agreed Newton's concepts, and today also we are using Newton's concepts in each and every place where we want to describe the motion. So today's chapter name is Laws of Motion described by Isaac Newton. Okay, now let us discuss about 2 things in this chapter. One, rest, and 2, motion. So what is rest and what is motion? Rest is defined as if any object you take and this object is not changing its location with respect to time, then we say that that object is at rest. For example, take a ball, it is at point A, and you're observing the ball at a point A for a long time, for 2 hours, for 3 hours, for 1 day, for 2 days, 3 days. Then you say that ball is at rest. So rest state can be defined that if that location is not changing with respect to time. But if the location is changing with respect to time, then what it is called? It is called motion. say the same ball, initially it is at A, after t equal to 1 second, now it is at B, and after t equal to 2 seconds, the ball is at C. So for different timings, the ball is changing its location, A to B, B to C. Then we say that the ball is in motion. Okay, so the body which is not changing its location with respect to time, then it is said to be at rest. The body which is changing its location with respect to time, then we say it is in motion. Okay, we understand. But one point you want to understand, rest and motions are relative. I think you heard this word in the previous chapter. Yes, rest and motion are relative. Relative means for one observer, if the body is at rest, but to the another observer, the body is in motion. In the last chapter, I have given an example of two passengers traveling in a bus, and there is an observer standing at the roadside and observing the bus. And take another example here. Suppose we are on the earth and we feel that we are at a rest state. Suppose I am standing here and you are looking at me, you feel that I am at rest state, and I am also feeling that you are at the rest state and watching this video. So each and every one we can say that we are at rest on the earth. But if you have observer in the planet Mars, then that observer do not feel that we are at rest, because according to planet Mars, the earth is rotating and we are also rotating with the earth. So according to that observer, we are in motion. So according to us, we are at rest, but according to the observer on the Mars, we are in motion. So that's why rest and motion both are relative. For one observer it is rest, for to the another observer it is in motion. Now move on to the deep into the topics. Inertia. Earlier I told you that inertia is the word introduced by a Galileo scientist. What is inertia? He told that it is tendency of a body to be in rest or to be in uniform motion. This was the definition given by Galileo. What it means? Suppose you are sitting on a chair for a long time and some of your friend comes and says that stand immediately. Then you can't stand immediately because your body is suited in the rest state. That is what called tendency. Suppose a person is running or jogging and you go to him, suddenly say that stop jogging or stop running. Immediately he can't stop because the body is habituated with the running state or habituated with the jogging state. So that is what called inertia. So whenever in the rest state, the body wants to be in rest. Whenever you are in the motion state, the body wants to be in motion. This is what called tendency of the body, and that tendency is called inertia. Now Galileo, after defining this, we have understand that we have two types of inertias. Number one, inertia of rest. It means body wants to be in rest state. Wants to be in rest state. Take an example. You can do at home also. Take a container, a glass tumbler filled with water, and on the glass tumbler there is a cardboard. On the cardboard there is a coin. It's a coin. Now it is in the rest state. Whole the system is in rest state. Coin, cardboard, glass tumbler filled with water. Whole the system is in rest state. Now I pull the cardboard in this direction. Then what happens? See, I am pulling the cardboard suddenly, not slowly, suddenly. Then in the next state, the cardboard comes in the direction of the pulling direction, and the coin will fall into the water. Why? Because coin wants to be in the rest state. As soon as you pull the cardboard, as it wants to be in the rest state, it in the same location and immediately falling into the water. So it's the best example for inertia of rest. Now take another example. You are in a bus. Okay, this is bus platform. Okay, and you are standing on the platform inside the bus. So bus is rest state now. Now the bus driver suddenly started the bus. Then what happened? When the bus driver suddenly starts the bus starts moving, and the lower part of your body also starts moving. But if you see this upper part, still it wants to be in the rest state, and so the lower part move in the forward direction because of motion of the bus, but the upper part wants to be in the rest state. Then what happens? This upper part in the same state, so you fall backwards. So this is called falling backward. So this type of experiences you will get many times in the bus or in the car or on the bike. This is the example for inertia of rest. Now the second type, inertia of motion. This means body wants to be in motion. Take an example. There is a fan having blades, and the blades of the fan starts moving as soon as you switch on. When you switch on, the electricity passes to the fan and the blades are rotating. You get the air. Now when you switch off, then what happens? Immediately electricity stops, and when the electricity stops, immediately the blades also should stop, but they're not stopping, they keep moving because they are in motion and they want to be in motion. So that's why when you switch off the fan, the blades do not stop immediately. It will take some time to stop. So this is the example for inertia of motion. Now take the second example, the same bus example. I guess you are thinking that what is the example. Now take the same bus, the platform. Now again the person is standing on the platform. Now this time the bus is actually moving in the forward direction. So when this bus is moving in the forward direction, this passenger also moving with the same speed of the bus. Now the bus driver suddenly apply the brakes. Then what happens? Bus stops, and the lower part of the person, as in contacting with the platform, it also stops. But upper part wants to be in motion, so the upper part move in the forward direction. Then what happens? You fall forward. You fall forward. This type of experience also you got many times when you're traveling in the bus, and this is another example for inertia of motion. Now we move on to a little more deeper into the topics. Balancing forces. So what is meant by balancing force? Take a block of mass m, and there are two forces acting on the block. One force F1 acting towards right, one force F2 acting towards left, but both are equal and opposite. Equal represented by equal to symbol, opposite represented with the minus symbol. Both are equal and opposite. Then what happens? Implies, take F2 this side, F1 plus F2 equal to 0, which is called, this is called net force. So the net force acting in the body is 0. Whenever net force acting on the body is 0, then these two forces are called balancing forces. So F1 comma F2 are balancing or balanced forces. So these are balanced forces because the net force acting on the body is 0. That means even the two forces are acting on the body, there is no effect on the body. Like you are in the rest state, sitting on a chair, and one person pulling in this direction, another person pulling in this direction, but still there is no effect on you because the resultant forces is 0. Is only possible whenever F1 equal to F2. Okay, so whenever the balancing forces are acting on the body in which state it is previously, it is also in the same state after applying the balancing forces too, because net force acting on the body is 0. But if net force is not equal to 0, take another example, the block M. This is the force F1 acting towards left, force F2 acting towards, force F1 acting towards right, F2 force acting towards left, and F1 is greater than F2. Then what happens? Then there is a resultant force which is F1 minus F2, because F1 is greater, F2 is smaller, so the resultant force is F1 minus F2 act on the body, and the body moves in right side direction because F1 is towards right. If F2 is greater than F1, the resultant force is F2 minus F1. In that situation, the body moves towards left because F2 is towards left. Okay, so this F1 minus F2, I told resultant force. This is also called unbalanced force. So why I have introduced this F1 minus F2 unbalanced force? Because I want to say that if you say a body is in motion because of force, maybe you are wrong. You have to say that body is in motion because of unbalanced force, because unbalanced force only gives the effect of change in state of the body. In this balanced force, take an example like tug of war. Many times you play this tug of war in so many different types of events happened. Like say this is a rope and there is a reference line, there's a point here, and different, like this side one person, this side two persons pulling the rope towards left side, and there is another person standing on the right side and pulling the rope towards right side. This is what called tug of war. So here the rule of the tug of war. Suppose the rope is moving towards left side, then you can say that left side force is greater than right side force. If the rope moves towards right side, then the right side force is more than left side force. And if the rope is not moving and the point is exactly below the reference line, then we say that the left forces equals to right forces, and we can say that net force equal to 0. So no force acting on the rope. Right, so we learned about what is balancing force and unbalanced force. Now we move on to some numericals based on resultant force. Right, say there's a block M of mass M, a force acting on the body in this direction, say a force F1 equal to 2 newtons. See, I have introduced the unit of force, Newton, because at Newton first time told about force, we are taking his name as unit for the force. So force SI unit is Newton. So F1 equal to 2 newtons, and another force is also acting, F2, which is equals to 2 newtons. Now what is net force? So I told you that net force is nothing but both forces are acting in the same, both forces are equal and acting opposite directions, hence F net equal to 0. So body doesn't have any effect. Okay. Now second one, take the same body of mass M, and this time F1 equal to 2 newtons and F2 equal to 2 newtons. Then what is resultant force? What is resultant force? Whenever two forces are in the same direction, you have to add the forces. means F1 plus F2 is now 2 newtons plus 2 newtons. This is nothing but 4 newtons because in the same direction. Now take another example, body of mass M. So this force F1 equal to 3 newtons and this is F2 equal to 5 newtons. Then what is resultant force? Resultant, net force, both are same. So resultant force is what? If you see, if you compare the previous example I told you, here which force is greater? F2. Therefore resultant force is F2 minus F1. So 5 Newton minus 3 Newton, this is nothing but 2 newtons, and you have to tell the direction. This is towards left. Remember, force is also a vector. You have to tell the magnitude and direction both. Now see this example. Guess what is the answer for this? F1 equal to 1 Newton, F2 equal to 3 Newton, F3 equal to 6 Newton. Tell me what is the answer for this? Yes, F1, F2, F3, all three are in the same direction. So the resultant force is nothing but F1 plus F2 plus F3 are in the same direction. So 1 Newton plus 3 Newton plus 6 Newton. So this is nothing but 10 Newtons. Now see the another numerical based on resultant force. Again there is a block of mass M, a force acting on it like this, F1 equal to 3 newtons. Another force is acting like this, F2 equal to 4 newtons. Then what is resultant force? Resultant force. This is a little different numerical comparing to previous numericals. These two forces are not parallel, these two forces are not opposite. But these two forces, if you observe carefully, both are perpendicular to each other. How could you say? See this line, draw the line like this. This is what, 3 newtons. And this is downwards, draw this line, downward, 4 newtons. Now you can understand the angle between them. This 3 Newton force and 4 Newton force is 90. Then what would be the resultant force? So the resultant force is this one. And this resultant force you can get using Pythagoras theorem, as it is a right angle triangle. So resultant force, F resultant equal to square root of 3 square plus 4 square. So 9 plus 16. So this is root of 25, which is 5 newtons. So the answer is 5 newtons. Now what is the direction? See the direction? This is the direction. Now what is this direction? To know, draw earth directions: east, west, north, south. Now see this arrow going like this. When this arrow going like this, you can say this is south east direction. All right. Now see this term we use many times in our daily life. Weight. Weight of a basket is 2 kg. Weight of bananas are 3 kg. Like this 4 kg, 5 kg. We say this weight many times in our daily life. But actually what is weight? If you observe carefully, when we say weight of a bag is 2 kg, actually we are not saying the weight, we are saying the mass of the bag. 2 kg. Kg is the unit of mass, not for the weight. Then what is weight? Weight is, it is gravitational force. It is gravitational attraction by the earth. So it is the force. When it is a force, we know the Newton's second law of force, F equal to ma. And just replace A with G. G is acceleration due to gravity. Implies now force F equal to mg, and this is what called weight. So weight is a force and weight formula is mg. Example, suppose there is a mass, there is a ball whose mass is 2 kg. Then what is its weight? See, weight I am using the symbol WT. Then weight is nothing but m into g. So 2 into g. G value you can take 9.8 or you can take 10. So it is nothing but 20 Newton. Why I have mentioned Newton? Because weight is nothing but force. So force unit, weight unit, both are same. Now see another one. If I say 1 kg weight equal to dash newtons, how do you find? Simply use the formula. Weight equal to m into g. 1 kg weight, 1 kg, so mass is 1 kg, g is 10, so it's nothing but 10 newtons. So 1 kg weight equals to 10 newton. So if I say that my bag's weight is 3 kg, that means it is 3 kg weight, then what is its original force? 3 kg into 10, that is nothing but 30 newtons of the weight of the bag acting downwards towards the earth. Okay, next example numerical. There is a block which is at point A and it started its journey with initial velocity 0.1 meters per second square and it gains final velocity v equal to 0.5 meters per second square in time 3 seconds. If mass of the block equals to 2000 grams, then find force acting on it. Right? So we know the formula F equals to m into A. We know the mass 2000 kg. Remember, this is not a SI value. 2000 kg, 2000 grams should be converted into SI unit kg. So 2000 grams is nothing but 2 kilo g, means 2 kg. Okay, we got mass. What about acceleration? Acceleration is not given, but you have u, v, t. Recall the acceleration formula. A equals to v minus u by t. So F equilibrium is the first equation. Now see the second equation, A equal to v minus u by t. So v is 0.5, u is 0.1, by time is 3 seconds. So it is 0.4 by 3. So it's nothing but 0.13 seconds. Therefore, F equal to mass is 2 kg into 0.13. It is nothing but 0.26 Newton approximately. Approx. See the next example numerical. If this car moving on the road with the force F equals to 20 newtons and there is a force acting in opposite direction between wheels of the car and the road, and this force is opposite that force, and this force is 2 Newton, and this force is called frictional force or friction. So frictional force always acting opposite to applied force, and frictional force is a contact force. It only exists when two bodies are in contact. Here wheels of the car and road are in contact, and so friction is developed. Okay, now my question is, if the mass of the car m equals to say 2000 kg, mass of the car is 2000 kg, then find resultant acceleration due to F and small f. Why I said resultant acceleration? I can say directly acceleration. Resultant acceleration because this car is not experiencing 20 Newton. It is experiencing two forces, F and small f. Therefore, it experiences the resultant of F and small f. So the resultant force is nothing but capital F minus small f. Why I have subtracted? Because this force is opposite to that force. So the resultant force is 20 Newton minus 2 Newton, which is 18 Newton. Now with this resultant force, the car is moving the forward direction. Therefore, acceleration A equal to F resultant by mass. So F resultant is 18 and mass is 2000 kg. So therefore, 2 9s are 9 by 1000, 0.009 meters per second square. So that is the acceleration of the car. So whenever the two forces are acting on a body, always you have to be considered the resultant force.